Okay, first we have this problem from topic 5. This is from the 2019 paper 2. It is paper 2 question from topic 5. We have a proton that is moving in a uniform magnetic field, and the magnetic field is directed into the plane of the paper. The arrows show the velocity of the proton at one instant, and the dotted circle gives the path followed by the proton. We see that that's a circle. And the first question says, explain why the path of the proton is a circle. Well, we can look at the force on the proton. The proton, so it's positive, so we have our conventional right hand rule. And if I were to lay my right hand so that my fingers point in the direction of the velocity vector, which right here is up, and then I curl my fingers in the direction of the magnetic field. The magnetic field is into the plane of the paper, right? The fletching of the arrow is going into the plane of the paper. Then what's going to happen is my thumb is going to point this way to the left. If I were to look at a different point, say the point up here, well, up here what's going to be happening is I'm going to have my velocity vector is going to look like this. Being constantly over here, for example, when my velocity is upward and my force is to the left, it accelerates, it's going to veer to the left. It's going to be pulled to the left. Eventually, it's going to be pulled to the left so much that it's going left. When it's going left, let's look at the force now. Well, I lay my right hand along where my fingers point with the velocity. So the fingers on my right hand are pointing now to the left. And again, I curl my fingers into the plane of the page because that's the way that the magnetic field hasn't changed. It's still that way. And now I find that my thumb is pointing down. And anywhere I go, if I look at the linear velocity, which is always going to be perpendicular to the circle at any point, then the force is always going to be centripetal. It's always going to be towards the center. So that is why it's circular motion. It's always pointed towards the middle. And when I have a force that's always pointed towards the center of a circle, then the object experiencing that force moves in a circle. It's circular motion. A few other answers that you could put here say the magnetic force is to the left at the instant shown. I don't know if that explains exactly why it's in a circle, but it does. It will go to the left. The force is to the left. The particle will move to the left. Explain a rule to determine the direction of the magnetic force. The force is perpendicular to the velocity, right? That's always the case, right? Because it's a cross product actually. And the force is constant in magnitude. The force is a centripetal force towards the center. This is the one that I think I would use. But all of these are acceptable. We can also, wherever you have the word force, you could also say acceleration. Of course, they're in the same direction, aren't they? So now that we know that we're moving in a circle, and we know why we're moving in a circle, because the acceleration is always perpendicular to the velocity and pointed towards the center of a circle, we want to find the radius of that circle. And in order to do that, we're given the speed of the proton and the magnetic field strength B. From these two things, we know that we can calculate the force. The force of a moving charge due to a magnetic field, F, is equal to QVB. But I also know from here that it's a centripetal force. So force is also equal to mv squared over r. So I can equate these two things and solve for r because I have everything I need. I know the charge on a proton. I'm given the velocity. One velocity is going to cancel, but I'm still given the velocity is here. And then I have the magnetic field strength here. So I can calculate r. I also know the mass of a proton that's given in the formula booklet. Okay, so I can take these two things and equate them. That's what's been done right here. F equals QVB, and F is also equal to mv squared over r. So I get QVB is equal to m squared over r. One of the velocity cancels, right? And so what I'm going to get is I'm going to get that r is equal to mv divided by qb, okay? And so the mass of a proton is given here. This is from your formula booklet. The velocity was squared, but one canceled, so here's the velocity, 2 million meters per second. The charge on a proton, or an electron, in this case a proton, is positive, and then the strength of the magnetic field. When we do this, we get let's see, we're going to get, let's go ahead and calculate this out. 1.67 times 10 to the negative 27th power. And this is going to be times 2 million times 10 to the 6th. And then this whole thing going to be divided by the charge and the magnetic field. So that's 1.6 times 10 to the negative 19th. And then that's times 0.35. And this whole thing here gives us 0.0596, which is about 0.6, 0.06. And that's what they ask for. Okay? Calculate the time for one complete revolution. One complete revolution is going to be 2 pi r will be the distance traveled, and we know the velocity already. So here we have an equation for the period, and the period is going to be equal to the distance traveled, the time. Time is going to be equal to distance over rate, and so we've got 2 pi r over v, and we know everything here, especially since we just calculated r. So I'm going to get 2 times pi times this number that I got for r divided by 2.0 times 10 to the 6th. Okay, so let's see what we get over here. We've got 2 times pi and then divided by 2 million. So we take our answer. We take the answer that we had here, and we divide it by 2.0 times 10 to the 6th power. And I forgot to multiply. I needed to multiply the answer by 2 pi as well. So I got 2 pi times the radius and then divided by 2 million. I divided by 2 million, but I need to multiply this thing by 2 pi. Okay? And when I'm done here, I get this answer here, 1.8737 times 10 to the negative 7th, 1.837, 1.8737. And that is to 2 sig figs, the same thing we get here. Finally, explain why the kinetic energy of the proton is constant. Well, the kinetic energy is constant because the velocity is constant. The magnitude of the velocity is constant, at least for circular motion. What we have for the same radius, we're going to have the magnitude of the velocity remains constant. The direction of the velocity continuously changes as the particle bends around to follow a circle. But since the magnitude of the velocity is the same, or the speed is always the same, then the kinetic energy is always the same, 1/2 mv squared. And so now here this talks about, alternative 1 says the work done by the force is a change in kinetic energy. Yeah, okay, so the force is always directed towards the center of the circle, and the velocity is always perpendicular. So F dot D is equal to 0. The cosine of the angle between these two is 90. So there's no work being done, so there's no change in energy. But I think I like alternative 2 better. This is a constant. The magnitude is a constant. So 1/2 mv squared is always going to stay the same. I think I would go with this one. But either one is acceptable, and that is number 1.